Hello and welcome to section 6.2, our second section in chapter 6. And this section deals with entropy. Our last chapter, or our last section, dealt with enthalpy, which was the heat of a system. This time, though, we're going to talk about entropy, which has in high school chemistry and in general chemistry has a very simple explanation, which is that entropy is the measure of chaos, right? That's what we all said. I know that's what my teacher said, but it has a more nuanced definition than that, because really entropy is the definition, or is the description of probabilities and chaos at the same time. Because my teachers used to always give the example of a messy room. And they would say that a messy room becomes clean, and you're putting in work to go away from the chaos of a messy room. So if you do work and clean your room, then you're decreasing the entropy of a state, and it takes energy for you to do that. That is half right, because what we're thinking about it too simplistically when we use that analogy. What we really should be saying, as a more accurate description, is that all the stuff in our room has a much higher probability of being out and being used and perhaps on the floor by itself than it would being put away nice and clean and never touched. And so by us moving something into a place that it wouldn't typically go, that is changing the probabilities of where that item could be. And that's what takes energy to do. So you can imagine this um, sort of, you could maybe change what we say about entropy to say that instead of entropy, chaos is always increasing. We could say the probabilities of higher energy states of order are always increasing. Free gas expansion is one very good example of this, because if you start out with two chambers connected with a valve, and initially you have all these gas molecules in one side, they're going to sit, as long as the valve is closed, it is the same energy for them to sit on the left side and do nothing, just bounce around, fly around in the flask. But as soon as you open this valve and give those gas molecules free reign to diffuse in and out as they please, the most probabilistic outcome, the highest chance state, is that you have some even mixture between the two. With the valve open, it is an extremely low probability that all the gas remains on one side. And by extremely low, it doesn't happen. And the reason why it doesn't happen is because entropy is always moving towards the most probable thing. That's why flipping a coin always converges to whatever probability is present for that set of outcomes. So if you flip one coin one time and you get heads, that's 100% probability you got heads. But if you flipped one coin a billion times, you would converge very quickly to 50% probability of having heads or tails, because entropy says that the highest chance outcome should occur. And that is why rooms get messy, because it's much higher chance that things end up out from their places and not put away. So that's kind of the qualitative, like narrative description of entropy. We can also talk about it in terms of math, saying that the total entropy of a system is equal to the system that you're talking about. Or sorry, total entropy in general, not of a system. Total entropy in general is equal to a system that we're mentioning, such as inside these two connected flasks, as above, or the surroundings, which is all the stuff around the flask. And for this class, mostly, we're going to stick with our talk of, or at least for now, we're going to talk mostly about the system, because it's a lot easier to talk about what's happening inside of a flask, like our reactions, than it is to talk about what's happening outside the flasks because of the reaction. So we'll typically leave surroundings as 0 and focus on the system. To have a spontaneous reaction, meaning the reaction can occur, all that's required is that the entropy increase. Examples of entropy increasing in a chemical reaction are something like this, where you have XY going maybe by homolytic bond cleavage to X plus Y. We've gone from one molecule to now 2 molecules in the products. This increases the entropy of a system because one molecule can exist in a state, but 2 molecules can exist in more than one state, in more than one place. And so the probabilities get changed, and there's a higher probability of a lower energy state here. So the entropy of the system increases. Another way entropy can increase is if you have some shape, some ring, and now your X and Y are up here, and in our reaction, we break that ring, maybe this time heterolytically, to make a larger acyclic molecule. The acyclic molecule is larger and can be like floppier. It takes up more space overall. And so it's going to provide more types of states for this molecule to exist in than the original ring, because of its size. And because of that, the entropy will also increase here. So entropy is honestly not the easiest of concepts to grasp, but hopefully this has helped a little bit. We're going to talk about both entropy and enthalpy in the next sections to try and describe a little better how chemical bonds can form and the energy behind their forming and breaking. This has been section 6.2.